Okay, we're at the top of the hour. I think we should go ahead and get started. First of all, let me say hello and welcome to today's webinar on Mastering Spice Simulation in Altium Designer. My name is Alexander. I'm a technical marketing engineer with Altium. And with me today, we have Kirsch Mackey, who is an electronics instructor at the University of Arkansas, as well as the business owner of, hopefully I'm saying this right, Hasofu, which provides hardware, firmware, and software development and testing. In this webinar, we will discuss the challenges that designers face when they ignore circuit simulation in their design process, the growing need for simulation in various applications, and the advantages that simulation offers in terms of design iterations, reliability, debugging, and cost savings. We will also explore some popular circuit simulation techniques and provide practical tips for effective simulation. Hopefully by the end of this presentation, you'll have a deeper understanding of why circuit simulation is essential in today's electronics industry and how utilizing Altium's SPICE simulation solution can help you create better products and avoid potential issues. So let's go ahead and dive in and explore the world of circuit simulation. Before we get started, I do want to mention the Altium 365 public workspace. And in this public workspace is where you can view a recording of today's webinar. You can download webinar-related files, register for upcoming webinars, and also take a self-guided tour of Altium 365. Now, this is a public version of our workspace, so it doesn't have all the bells and whistles that a standard pro or enterprise level subscription has, but I do think it is a good starting point to understand what the workspace is and how it can be a benefit of you or to you and your team. So here is the agenda for today's webinar. First, we'll discuss the typical yet painful process that some hardware engineers go through using a standard approach to hardware design. Second, we'll explain the need for circuit simulation to be included in the hardware design process to help reduce the issues faced in the typical design cycle. We discuss real-world examples of companies who skipped simulation when they had the option and how that backfired for them. Third, you'll learn about the specific advantages circuit simulation has for anyone who wants to use it. And fourth, we explain the different simulation techniques used to predict circuit behavior and keep your design out of trouble. Next, you'll get tips on how to improve your circuit simulation skills so they work for your design environment. Number 6, we'll go into a demo where we'll look at some circuit simulations that you can perform to fix common problems in your circuit analysis. And then lastly, we'll do a Q&A session with Kirsch to address any questions you might have. So let's go ahead and get started. So now let's talk about the issues in the typical hardware design cycle. And the first thing I want you to do is imagine you're flying a plane and you suddenly realize that there are some critical issues with the aircraft that you didn't catch during the pre-flight checks. Now, this is a pretty scary thought, right? One might wonder who did the testing or who'd even let the aircraft come off the ground without making every check possible that it would work as intended. Unfortunately, this is a situation that many hardware designers find themselves in, trying to fix problems after the design is already in motion. Consider the consequences of a delayed product release that can stem from neglecting circuit simulation. In fact, that's what happened to one customer in the US, where they didn't spend the extra week to simulate everything in the design from the top down. They considered their design to be relatively straightforward, just consisting of analog to digital converters, relays, and some LEDs. So it was fair that they wouldn't expect to have to simulate it. Unfortunately, despite their best efforts in design reviews, mistakes had made it through to the PCB layout. And that put them in a tough situation where they missed their shareholder deadline by, coincidentally, 1 week. but they didn't have enough time to respin a new design, and as a result, they pulled the project, lost millions of dollars in funding for that year. What's unfortunate is that stories like these, while maybe not always as extreme, are still frequent enough for this to be a major issue in hardware design cycles. And as electronic systems continue to grow in complexity, designers face numerous challenges when they disregard circuit simulation in their design process. Let's look at some of the issues that can arise as a result. It goes without saying that multiple hardware iterations of the same product leads to increased design costs. The costs are in the board materials, components, and manufacturing and work hours, and inevitably cause delays in the project schedule. Naturally, these delays cause a trickle effect as you scramble to make the necessary changes and reevaluate your design. Delays impact your product's time to market and ultimately affect your competitive edge in the industry. Design reliability and performance are also at risk when you don't incorporate circuit simulation. An untested design is more prone to failure or subpar performance, which could then lead to a customer not being satisfied and tarnish your customer or your company's reputation. Furthermore, failing to simulate your design might also result in non-compliance with industry standards, creating legal and financial repercussions for your company. And lastly, neglecting simulation can erode customer confidence in your product should it ever get to production. When customers encounter problems with your device or system, they may lose trust in your ability to deliver reliable and high-quality solutions. And this can have a long-lasting impact on your brand and your company's long-term success. In summary, ignoring circuit simulation in your design process can lead to a myriad of issues, including increased costs, delayed product releases, unreliable performance, non-compliance with industry standards, and loss of customer confidence. But by incorporating simulation into your workflow, you can avoid these pitfalls and ensure a smoother, more successful design process. The need for circuit simulation in modern PCB design cannot be overstated. With electronic systems becoming more complex and sophisticated, designers must ensure their designs are reliable, cost-effective, and efficient. Let's briefly explore 3 key factors driving the need for circuit simulation in today's electronics design landscape, along with real-life examples of how circuit simulation can make or break a project. First, the growing complexity of electronic systems presents significant challenges in terms of design, layout, and component selection. Circuit simulation allows designers to evaluate their designs, optimize component values, and identify potential issues before they become costly problems in the prototyping or manufacturing stages. For example, in the power systems engineering field, rigorous simulations are performed to identify potential failure points in the power grid before any construction begins, and this ensures a reliable and robust infrastructure. Conversely, some hardware designers might skip the simulation step and rely on back-of-the-napkin or engineering paper calculations. This can lead to expensive and time-consuming board respins, debugging, and troubleshooting, as illustrated by a case where a simple error in a cable drawing led to 72 hours of troubleshooting to find the issue. Second, design reliability and cost considerations are critical in today's competitive market. Companies must balance performance with cost, and circuit simulation plays a vital role in achieving this balance. By simulating your design, you can identify areas for improvement, optimize component choices, and ensure that your design meets the necessary performance and reliability criteria without breaking the bank. Unfortunately, not everyone appreciates the importance of circuit simulation. Take, for instance, a company where a manager decided to prioritizing saving $12,000 and 1 month to not get simulation packages and training done for their system engineer. That was a mistake. That led to an extra cost of 6 months and $150,000 from failed tests on EMC and UL certification for their product. And then once they found the problem, they spent an extra $50,000 to respin the boards. So here's the thing. Time to market pressures continue to mount as companies strive to stay ahead of the competition. Circuit simulation helps accelerate the design process by enabling faster design iterations and early identification of potential issues. This not only saves time, but also reduces the risk of costly redesigns and delays in the product release. The growing complexity of electronic systems, design reliability and cost considerations, and time to market pressures makes circuit simulation an indispensable tool in the modern PCB designer's toolkit. By embracing circuit simulation, designers can avoid the costly mistakes and delays that plague projects lacking proper simulation and analysis. Building on the importance of circuit simulation, let's discuss some real-world scenarios and use cases where simulation plays a crucial role in ensuring the success of a project. First, consider high-speed digital designs. These designs often involve multiple high-frequency signals, which can lead to signal integrity issues and crosstalk between the traces. Circuit simulation allows designers to analyze signal integrity, determine the need for termination resistors, and predict reflections before committing to a physical layout. This helps avoid costly redesigns and ensures optimal performance. Next, mixed signal designs, which combine analog and digital components and often present unique challenges. Simulation plays a vital role in understanding the complex interactions between these components and verifying that the entire system functions as intended. For example, designers can perform sensitivity analysis to determine the impact of component tolerances on an ADC's performance, helping to optimize the design and ensure accurate signal conversion. In power electronics and high-power applications, managing power dissipation, thermal performance, and efficiency is critical. Circuit simulation can help designers identify areas of high power dissipation, predict switching losses in a flyback converter, and optimize component values for improved efficiency. This not only results in better performing designs, but also reduces the risk of thermal issues or component failures. And lastly, RF circuits demand precise control of signal frequencies and phase noises. Simulating RF designs, such as Colpitts oscillators, allow engineers to assess the impact of component variations on frequency stability and optimize their designs to achieve the desired performance. Monte Carlo analysis, in particular, can be instrumental in understanding the effects of component tolerances on the overall circuit behavior. As you can see, circuit simulation is essential across a wide range of applications, including high-speed digital, mixed signal, power electronics, and RF designs. By incorporating simulation into your design workflow, you can identify potential issues, optimize performance, and increase the reliability of your designs in these critical areas. Now that we've seen some real-world scenarios where circuit simulation is essential, let's discuss the key advantages of incorporating circuit simulation into your PCB design process. First and foremost, circuit simulation allows for faster design iterations. By simulating your designs, you can identify and address potential issues early in the design process, significantly reducing the time spent on troubleshooting and debugging later on. This enables you to refine your designs more quickly, leading to a faster overall design cycle. Next, circuit simulation improves design reliability. When you simulate your design, you can analyze its performance under various conditions and ensure that it meets all the necessary specifications and industry standards. This helps prevent unexpected failures in the field and contributes to building a reputation for reliable, high-quality products. Another advantage of circuit simulation is that it simplifies debugging and troubleshooting. When you encounter issues in a physical prototype, it can often be difficult to pinpoint the exact issue. Circuit simulation allows you to isolate potential problem areas in your design and can address them before building any sort of physical prototype. This makes it much easier to identify and resolve issues. And finally, circuit simulation can lead to significant cost savings. By identifying and addressing potential problems early in the design process, you can avoid costly board respins, reduce the need for existing prototyping and testing, and minimize the risk of delays in product release. In addition, simulation can help you optimize component selection and placement for improved performance and cost effectiveness. In summary, circuit simulation offers numerous benefits to PCB designers, including faster design iterations, improved reliability, easier debugging and troubleshooting, and also cost savings. By integrating circuit simulation into your design workflow, you can create better performing, more reliable, and cost-effective products. When it comes to circuit simulation, having the right technique at your fingertips is critical for tackling the diverse challenges that come with modern PCB design. Today, we'll explore some popular simulation techniques that can help you uncover potential issues, optimize performance, and bring your designs to life with confidence. First, let's talk about transient analysis. This powerful technique allows you to simulate the dynamic behavior of your circuit over time. By analyzing how your design responds to changes in inputs, loads, and other factors, you can ensure that it performs optimally under real-world conditions. Pole zero analysis is an important circuit simulation technique that helps designers to evaluate and optimize the stability and performance of their circuits. By analyzing the location of poles and zeros in the transfer function of a circuit, engineers can identify potential stability issues and take corrective action before the circuit is built. Pole zero analysis can also help designers to optimize the performance of their circuits by identifying opportunities and improve gain, bandwidth, and other key parameters. Next, we have AC/DC analysis. This essential tool helps to examine the steady-state behavior of your circuit under both alternating current and direct current conditions. And by understanding how your design operates across different voltage and current levels, you can fine-tune its performance and ensure that it meets required specifications. Now, let's discuss AC/DC sweep analysis. This technique enables you to investigate the frequency response of your circuit, revealing crucial information about its stability, bandwidth, and overall performance. With sweep analysis, you can efficiently identify and address potential problem areas in your design. Noise analysis is another vital simulation technique that helps you quantify and minimize the impact of noise sources in your circuit. By understanding how noise affects your design, you can make informed decisions to improve signal integrity and overall performance. Parametric sweeps and sensitivity analysis are essential tools for exploring how component tolerances and variations impact your design's performance. These techniques enable you to identify critical components and optimize your design for robustness and reliability. Finally, we have Monte Carlo analysis. This powerful simulation approach uses statistical methods to evaluate the performance of your design under a wide range of component variations and operating conditions. By assessing the impact of these uncertainties on your design, you can minimize risk and ensure consistent performance in real-world scenarios. And just to mention, there are also temperature sweeps that you can do on your components to simulate their behavior in harsher environments in Fourier analysis. Fourier analysis is a powerful mathematical tool, and that's commonly used in circuit simulation to analyze the frequency response of a circuit. And by breaking down complex waveforms into their individual sinusoidal components, engineers can better understand how a circuit will behave under different operating conditions and then make more informed design decisions. Fourier analysis is especially useful for analyzing total harmonic distortion in circuits and transformers to ensure reliability and performance of a system. This technique is commonly used in models for utility grid, for power system quality, and not just hardware design. In summary, these versatile simulation techniques provide valuable insight that can help you create more reliable, high-performance designs. By incorporating these tools into your engineering workflow, you'll be better equipped to tackle the challenges of modern PCB design and bring your innovative ideas to life. Now that we've explored the power of circuit simulation techniques, let's discuss some tips to help you maximize their simulation effectiveness and make the most of your design efforts. The first tip is to choose appropriate models and components. The accuracy of your simulation results depends heavily on the quality of the models and components that you use. You should use websites like Octopart to ensure that you're using up-to-date manufacturer-provided models whenever possible, and then verify that they accurately represent the real-world behavior of the component in question. Number 2, ensure accurate parameter values. Accurate component values are crucial for obtaining reliable simulation results. Make sure to double-check your component values against datasheets and manufacturer specifications. And don't be afraid to adjust them as needed to improve your design performance. Like the circuit simulation guru Steven Sandler says, a circuit simulation is only as good as the models being used in it. In other words, garbage in, garbage out. Number 3, utilize proper simulation settings. Take the time to understand and configure your simulation settings appropriately for your specific design goals. This would include selecting the right analysis type, defining appropriate input and output conditions, and specifying the required simulation time or frequency range. The next tip is to verify results with measurements and empirical data. While simulation is a powerful tool, it's essential to validate your results with real-world measurements and empirical data. The trick some engineers use is to go old school. You can order some familiar parts that are unfamiliar to you, then test them on a breadboard or a quick mini PCB. And you do this to verify that it should function as intended before moving forward with the full design. These kinds of steps help to ensure that your design performs as expected in practice and enables you to make informed decisions about any necessary changes or optimizations. The name of the game is to catch errors early, not after the fact. The next tip is that you can iterate and optimize easier the earlier you are in the design phase. In fact, circuit simulation itself is an iterative process. Use the insights gained from your simulation to identify areas for improvement, and don't be afraid to make changes to your design or even your components as needed. This iterative approach helps ensure that your final design is both robust and reliable, saving you time and resources in the long run. By following these tips and embracing the power of circuit simulation, you'll be well on your way to designing PCBs that perform optimally, meet industry standards, and ultimately exceed the expectations of your customers. Remember, effective circuit simulation is not just about having the right tools, but also about using them strategically to make the most of your design efforts. We have now covered the main topics of our agenda, so you should understand the importance of simulation and the types of simulations you can perform. Now it's time for a demonstration, and what we'll do, we'll show you the power of simulation and how it will improve the success of your designs. So here we are in Altium Designer, and I have a few examples here, and really what I want to go over is, well, those examples, but really how we can use Spice to make better design decisions. So let's first take a look at this circuit here, and this is really just a voltage divider with a cap over here. And the first thing I want to do is figure out the voltage and current at my different nodes. So I'm going to run an operating point analysis. First, let me run a verification, and the verification is just going to do an ERC and check that I have simulation models for all my components. Preparation, I have my DC source, and I will choose operating point, and I want to display on the schematic the voltage, power, and current. I'm not going to have pole zero analysis on yet, we will do that later. So let me go ahead and run this. And I'll have sim data, my sim data panel open, and from here I could add different information on here. So I could have my V in, V out, maybe power across R7, whatever it is. I could have that here. But of course, remember this should be displaying on my schematic. So I like this view better, just colorful and more visual in my opinion. So this is helpful if I'm doing maybe some part choice. So, you know, I know R7 is going to have to handle 1.389 watts. So when I'm going to look for my components, I need to look for a power rating that is able to handle this power. So the next thing I want to do is the pole zero analysis. And this is going to be helpful in terms of figuring out or understanding the stability of my circuit. So for my input node, I'll have in, output node out. My reference is going to be ground, which is 0. And I want to look for poles and zeros, and not just poles or just zeros. And my transfer function, that's in here. And let me go ahead and run this. And at the bottom, we'll click on the Pole Zero Analysis tab. And if we click on Pole, at the bottom here, it'll show me where my pole is at. This does not have a imaginary number in this expression. This pole is all real. And if we highlight, we can see where that is. Also, it's down here. And if you want, you could even zoom in, but really the value is what we have and what we're looking for. So this can really help you understand your circuit and its stability. So now what I want to look at is I want to understand how my output is going to change in relation to a variable R7. So for that, I want to do a DC sweep. And so I'll just, from the pull down, select R7. I'm going to vary R7 from 1 to 10, stepping by 1. And I'm going to have an output expression of Vout. So what am I measuring? I'm measuring Vout. To add that, just click on this Add button. You can type it manually, or if you press these 3 buttons here, you can find your Vout. I'll change the color to blue, something vibrant that we can see, and press Create. So now we're going to take a look at Vout as it relates to a changing R7. So let's run this, and we can see as we increase the resistance, the voltage across also changes. So we're going to have a higher voltage drop. So how is this useful to us? Well, let's take a look at this example over here, my strain gauge. So if I want to, let's say I want to find what value of R12 is going to make it so there is no difference, no voltage difference between these 2 points. For that, I'm going to do a DC sweep of R12 just like we did for R7. So let's again do this verification. For our preparation, we could add some probes. And if you're adding these probes, don't just do a voltage probe, as that is going to be relative to ground. We want to have these relative to each other. So we're going to do voltage difference, and we'll place one there and one here. Let's go ahead and change the color to something we can see, like a bright red. We're going to have a DC sweep again, and we're going to sweep R12 from 1 to 1,000. I think we're going to hit somewhere in between that range, and we're going to step by 1. And just to verify these probes, let's go ahead and add an output expression for Vout minus, or Vout plus minus, Vout plus minus Vout minus. So these two here. Maybe I should have labeled it, A and B, but that's something else. So let's go ahead and find Vout plus minus Vout minus. We'll add this as a blue, and we'll put this on a new plot just so we can see that it is the same, and it'll verify the probes. So if we run that, we can see these two are the same, so that gives me confidence everything's working as it should. Let's go ahead and delete this plot just to give ourselves a bigger viewing area. And what I want to do, remember, is find the point where I have a difference of 0 volts, because this graph is the difference between those two outputs, Vout plus and Vout minus. So let me go ahead and right click on this. I'll add a cursor to my graph, and I want to find where this crosses, and it should be somewhere around there. So let's move my cursor, and if you look at the bottom left of the graph here, I have my values for my cursor. So visually, you can just look at this. Let's zoom in just with a click and drag and see where this is crossing. Actually, it's really close. It looks that we're about 720. I could even zoom in even more. Yeah, and it looks at a resistance value of 720 ohms. That is the value I need for R12 to satisfy my circuit. So that's how DC sweep can help you find a component value you're looking for. Now let's go on to my other example. So in this example here, we have a Butterworth low-pass filter. My op-amp has a gain of 1, and previously, in the example we just looked at, we didn't know the values of the components, so we did a sweep to figure that out. Here we kind of have a general idea of what the values need to be. But for this, I want to see how the variation in component values affects my circuit. So the first thing we're going to do is do a transient analysis. So let's first start the verification. Here you see that well, we passed the ERC and my simulation models were automatically assigned. That's because these red components are generic components. Excuse me. And generic components are great for prototyping. They have a footprint, and if you go into their properties, you can just select from a pull down their values and start, just creating prototypes and layouts quickly. So we'll go to the preparation. I'll add a probe, a voltage probe, to my output here. And let's change this to orange. And we won't do a sensitivity analysis yet. We will first do a transient analysis. We'll go from 0 to 5 milliseconds, and we'll take a look at our input. So the voltage at V7, our input, and our output. We're going to look at both of those. So let's go ahead and run this. And this is kind of interesting. So we do have some attenuation here and also some shift going on. So let's further look at our circuit. So to look at the overall performance, we're actually now going to do an AC sweep. We'll start from 10 hertz to 5K, and we'll do 100 points per decade. Again, you could always add more points or less depending on the resolution you want, and I guess time to analyze. Higher resolution, I think, is always better. Well, anyways, for my output expressions, we're going to take a look at the magnitude and decibels of my output. And again, to do that, just click on these 3 dots here. For magnitude, I'll go to complex, magnitude, and from the pull down, I'll click on dB. And same thing for phase. So let me go ahead and run this analysis. Let me actually go back. I don't want to include that probe. So let's just close it. And we'll run this again. And if I want, I could have just right-clicked and removed it from the wave, or from the plot, but I just removed the probe and reran. So when I designed this filter, it was designed to have a cutoff frequency of 1000 hertz. So if I look at my magnitude, I could add a cursor, and I could manually move this to 1000, and again, I'm looking down here. Or I could just look at my -3 dB point, my cutoff point, and yeah, it's about, 1000, 997.43. That's good enough for me. That's 1000. So this looks good. It seems to be working as intended. just to talk about phase, since we do have it on here, we do have two y-axes. I have my phase, and for both I have frequency. So I have my magnitude, my phase, and you can see as my frequency increases, my phase changes, as well as my magnitude. So this looks like it's working fine, but what I want to know now is how my magnitude is going to change how sensitive the output is to changes in these varying component values. So for that, I need to do a sensitivity analysis. So I'm going to go ahead and check that on. And then to change the settings for that sensitivity analysis, I'll click on the settings button here. I'll go to the sensitivity tab, and I can turn on group deviations. Now, I'm going to take a look at resistor and capacitors, since that's what I'm dealing with here. And this 0.1 is 10%. And if I wanted to, maybe do a 20% variation, I could do 0.2 or, 0.5 for 50% variation. I'm just going to do 0.1. I'm going to keep that. I'm not going to have custom deviations. We could take a look at that later. So we're going to press OK and then run this analysis. So if we take a look at my magnitudes and focus at the bottom right here of this plot, we see the different combinations of my resistors and capacitors and how these different combinations give me a specific output, right? So I could start looking at these, and if I look at between S4 and S5, the resistors aren't changing, yet I'm getting a change in my cutoff frequency. So that's telling me that my capacitance is really changing this cutoff frequency. And if we want to add a cursor again, let's go to my 3 dB point, or my negative 3 dB point. We can see that I'm actually past this 1000 hertz. I'm at 1.1. So it seems that these capacitors are affecting they're pushing the cutoff frequency later. And actually down here, we'll notice that the resistors have the opposite effect. They're pushing it earlier. So if we want to take a closer look at this, we can go back here, and that's where we might want to look at custom deviations. So maybe specifically C4. So let's run that again, and we can see specifically how C4 is affecting my my output. So that is the benefit of using AC sweep and sensitivity analysis. So now let's take a look at the next example here, and that's going to be the notch filter. Sorry, not the notch filter. Let's take a look at the buck converter. So let's say you design a buck converter to operate at a specific switching frequency and a specific duty cycle. And you want to know what the input voltage range for this device is, but really more importantly, we want to reduce the ripple. So we want to know in time what the output ripple is going to look like. And for this buck converter, I didn't really do the calculations from scratch. I just did some rough calculations and chose some capacitor values. But with simulation, the good thing is that I can see what the performance is going to be like with these values and this pulse frequency. So let's go ahead and do a transient analysis on this. I have my output expressions. I have my V out and my RMS value for the output. And let's just go ahead and run this. And, oh, it's still going. Let's give this a second. Okay, so I think that's good. So before I take a look at any of the components, I just want to make sure that my initial buck design is sound. So let's just go ahead and zoom in here. Ooh, let's zoom in a little more. Actually, what's going on here? Ah, we have Monte Carlo. We don't want that. Let's run that again. There we go. Okay, so let's just fit the document just so we know the starting point. So this was the starting point, and I'm just going to zoom in on a section here. So my RMS value is supposed to be 3, which is what it's at. We'll just say this is 3. So that is fine, but my boss told me that my voltage ripple needs to be at 1% or less. So let's test where we're at, and let's actually bring up the simulation dashboard. Oops, popped up on my other screen. Let's drag that over. Not sure why that happened, but you know what? Sure, we'll leave it. I was going to close it, but I just brought it up. So let's bring up my cursors, and let me look at the peak and troughs. Okay, and I'll open up sim data, and looking at this, here is the difference between cursor A and B. We'll do 0.253 divided by 3 times 100. So we're at 8.4%, and we need to be at 1% or better. So we are definitely out of scope. So let's go back to our design and change this capacitor value. And let's run this again. Hopefully we get something better. Again, let's just fit this to the plot. It looks a lot better already. Let's zoom in. And let's actually zoom in again. And we'll do the same thing as before. We're going to add some cursors here. Let's go ahead and measure the difference here. So we'll bring up our calculator again, and this is 0.0029, right? 1, 2, yeah. Divided by 3 times 100. Oh, and this is great. We are under 1%, and that is within tolerance. So we're looking good. So now let's say that everything is good with this design, and we want to make thousands of this design. We want to produce them. So what we want to be wary of is the different or the varying values of my components, because when you get components, they're not always as labeled. For instance, a 100 ohm resistor, if you're ordering thousands and thousands of these components, maybe one will be 100, another one will be 97, another would be 103 ohms. So they're not all going to be the same, and that's true for capacitors, inductors, any other type of component you're using. So what we want to do is test the robustness of our circuit in the face of all these varying component values. And to make sure we're still in scope, we're going to use Monte Carlo analysis. And what that's going to do is it's going to randomly assign values for my different components and sources. And I guess if you're doing, thousands of boards, you probably want to have more than 10 runs of this analysis, but just for our example, we're just going to do 10. If I did 1,000, we would be here a little bit longer. So 10 is good to me. So let's go ahead and run this, this analysis. Okay, that is done. Again, let's fit the document. And if we zoom in, then we can see the upper and lower limit of the performance of my circuit. And then from here, we can do further analysis. And if you click on the values here, just like before, you can see the values of your components, or the, what's the word? The combination of the values of the components and the outputs that they're giving you. So really doing this type of analysis helps you to put a good product into the hands of your consumers, and it really builds the trust between you, your company, and your customer. So now let's move on to my next example. Actually, looking at the time, we are very behind. So what I will do is actually skip this last example, and we'll just go back to the PowerPoint for Q&A. Right before we do, let's just quickly go over our conclusion, which is circuit simulation can no longer be an afterthought, especially in today's designs and those trending going forward. It's really making it impractical and even risky to ignore circuit simulation. The cost and short time to apply this capability is really a small premium to pay for the insurance the analysis can provide against wasted development time, excessive costs, and difficult to overcome design pitfalls and patterns. So now let's move on to the Q&A. If you have any questions, please put those in the Q&A section of Zoom, and we will do our best to answer those. So thank you very much, and we'll take a look.